In this section, we will be combining functions a different way than we have so far. So far, we've added, subtracted, multiplied, or divided functions. And in this section, what we're going to be doing is composing them, or forming a composite function. So first, we'll just figure out the notation for this new process of composing functions, and then we'll look at finding the domain of a function that's a composite function. So we'll start with the definition. And it says the composition of f and g is defined to be, and it's this set of symbols. We'll write f circle g of x for the composition of f with g, and we will mean f with the input g of x. So x will go into g, and then the output from g will be the new input for f. And we can do this composition in the other order. We could do g circle f of x, or g composed with f. And in that case, x would first go into f, the inside function, and then the output from f would become the new input for g. We'll worry about the domains when we get into some examples, but it's just saying the domain of f circle g, or f composed with g, is the set of all numbers x in the domain of g, such that the output from g is also in the domain of f, and that can get pretty complicated. And again, here the idea is that x is put into the function g, or the inside function, and then the result, or the outputs from g, those are put into the function f as the new input for f. So let's take a look at some examples. In example 1, if f of x is 3x minus 5 and g of x is negative x squared, we want to just find the symbols for what f circle g of x would look like. So f circle g, or f composed with g of x, if we switch to just nested function notation, f is on the outside, g is on the inside. And what we want to do is replace g of x with its formula. So just write negative x squared where we have written g, but we want to leave f as f. So we want to do f of, instead of g of x, we'll write the pattern for g of x, which would be negative x squared. So we're just rewriting. Instead of saying g of x, we're going to say, but g of x is the same as negative x squared, so replace that. Leave f on the outside. And this is where it gets a little more complicated. So now this notation would be saying use negative x squared as the input for f, but use the pattern for f. F's pattern says take 3 times whatever and subtract 5. So if my input is negative x squared, I will do 3 times negative x squared, and I'll subtract 5. I can simplify that to negative 3x squared minus 5. I not necessarily simplify, but rewrite it in that form. So when I do f circle g, I get up to this formula, negative 3x squared minus 5. Let's also do g circle f. So if I want g circle f, or g composed with f instead, then when I switch to nested notation, f is on the inside. So we can think of that as happening first. So first x goes into f, and what happens to it? So we leave g written as g, but we replace f now. F of x, instead of writing f of x, we're going to write 3x minus 5 as the new input for g. So g of 3x minus 5. And then this notation says use 3x minus 5 as the new input for g. And the pattern for g says that g of whatever is the opposite of that thing squared. So this means we want to do the opposite of the input, which is now 3x minus 5, and we want to square that. Then order of operations would say that negative sign is really a multiplication by -1, but I would do the squaring first. So I'd have 9x squared minus 30x plus 25. If you need to FOIL that out, you can, but you should get 9x squared minus 30x plus 25. And then multiply the whole thing by -1, which means we're going to get negative 9x squared plus 30x minus 25. So obviously f circle g and g circle f are not the same thing. For one, we got negative 3x squared minus 5, and for the other, we got negative 9x squared plus 30x minus 25. So different functions. All right, so example 2 here, which is kind of similar. Actually, it's some simpler functions, but now we're going to think about the domain as well. So if f is just the linear function 3x plus 2, and g is also a linear function 4x minus 5, we want to find f circle g and g circle f, and then think about the domain for each one. So let's find the formulas first. F circle g, or f composed with g. F is on the outside, g is on the inside. So we can think of g happens first, and then we do f apply to the output. So we'd write f, leave it as it is, and replace g of x with its formula, 4x minus 5. So we can read this as f of 4x minus 5. F says take the input times 3 and add 2. So this x is being replaced with 4x minus 5. So I have 3 times this group, and then add 2. Right? So this whole group is being substituted for the x, because that group is g of x. Right, so that shows up as the new input for f. And we get then 12x minus 15, and then add 2, so 12x minus 13. G composed with f, on the other hand, would have g on the outside and f on the inside, so f happens first. So we would replace f with its formula, which is just 3x plus 2, and then put that as our new input for g. So we'll have 4 times this group minus 5, so 12x plus 8 minus 5, which is going to be 12x plus 3. So notice again, they're not the same thing. One is 12x minus 13. One is 12x plus 3. Okay. And now let's think about the domain of f circle g. So when we think of the domain of f circle g, first we're going to think, well, x has to first be able to go into g. So x must be in the domain of g. And then additionally, x must be in the domain of the formula for composition. In this case, that was 12x minus 13. We don't want to only look at that final formula, because we also know that x has to first pass through that inside function, that g function in this case. So g is the inside function. So it's like we have 2 steps to consider. First, we consider what's the inside function, And then we consider what's that final formula, and we want to make sure that x satisfies is in the domain of both pieces. In this case, the domain of G is all real numbers, because G is just linear. And we'll need this in the next step. The domain of F is also all real numbers, because F is just linear. And in this case also, the domain for that 12x minus 13 is also all real numbers. And the domain of 12x plus 3 would be all real numbers. So since there aren't any restrictions anywhere along the way, the domain for the composition will be all real numbers. In the second one, we would first consider for the domain of G circle F, we need x must be in the domain of F, the inside function. And x must be in the domain of 12x plus 3. Which, in this case, again, both are all reals, so the domain for F, G circle F will be all reals. This will be more interesting when we have some functions with restricted domains, but for this one, both compositions would have all real numbers for their domains. But we get this idea that there are two things to check: the domain of the inside function and the domain of the formula you come up with after you've simplified the composition. One more not too complicated example, and then one that gets a little complicated just because it has fractions, and fractions are always a little messier. So F circle G and G circle F. For this one, if f of x is absolute value of x and g is 3x minus 1, the composition of f with g, first we would switch to nested notation, replace g with its pattern, and then use that as the input for f. So we'll have, f says take the absolute value of whatever the input is. So in this case, the absolute value of 3x minus 1. And g composed with f. G on the outside, f on the inside. So f happens first, and then g happens second. Leave g, and then replace f with its formula, or its pattern, which is absolute value of x. And then this says use absolute value of x as the input for g. So we'll have 3 times the absolute value of x minus 1. And for the domain of f circle G, first we need x must be in the domain of the inside function, which is 3x minus 1. And that's linear, so its domain would be all real numbers. And also x must be in the domain of the absolute value of 3x minus 1, which is that formula we came up with at the end. And there are no restrictions there, so negative infinity to infinity. So the domain for this composition would be all real numbers, since there's not a restriction at any point along the way. And the domain for G circle F, x must be in the domain of the inside function, which is absolute value of x. And that would be all reals. And then x must also be in the domain of the final formula, which would be also all reals, because we can take the absolute value of anything and multiply it by 3 and subtract 1. There aren't any issues. So that domain overall is also all real numbers. And like I said, we're going to get to some examples here where it's not just all real numbers for the domain. The next one is going to be a situation where we have a restricted domain. This time, instead of just doing f circle g and g circle f, we're going to do f composed with g and then f composed with f, which will be a little bit different. And the functions are going to be just messier because they're fractions. So f circle g first, or f composed with g. F composed with g of x will be first nested f of g of x. Leave f as it is, replace g with its pattern, which is 1 over x minus 4. And so this is saying use 1 over x minus 4 as the input for f. So we take the structure of f, which is 1 over the input plus 2, and replace the input with 1 over x minus 4. And then we want to clear up that complex fraction. So multiply everything by the LCD of the denominators of each term. So that would in this case be x minus 4 over x minus 4. And that will clean up to x minus 4 over 1 plus 2 times the quantity x minus 4. And we can keep going, so we'd have x minus 4 over 1 plus 2x minus 8, which would be 2x minus 7. Then let's think about the domain before we move on to the next. Notice that if we just look at the final formula, x must be in the domain of x minus 4 over 2x minus 7, which means x cannot be 7 halves, or 3.5, because we can't have a 0 in the denominator. But because x has to go through g first, we also see that x can't be 4. Because g is the inside function. So g was 1 over x minus 4, so x can't be 4. So it's not because there's an x minus 4 in the numerator. That's not the problem. It's just that the input first goes through the function g, and then the output goes into f. So if we can't even make sense of g of the input, then we can't go on to the next step to put the output into f. So the domain would be the set of all x such that x is not 7 halves and x is not 4. So there are 2 values that have to be restricted. One coming from the inside function and then one coming from the formula at the end. Alright, so then let's also look at f composed with f. So we'd have f of x. So that's going to be f of 1 over x plus 2, replace the inside function with the formula. So here we're just replacing that one. And now we're using, this is going to seem strange, using 1 over x plus 2 as the input for f. So we use the structure for f, which is 1 over the input plus 2, but the input is also 1 over x plus 2. So we again want to clear out the fractions, clear up the complex fraction. So we'll multiply the whole thing by x plus 2 over x plus 2. And that's going to give us x plus 2 over 2 plus, well, it's not right, over 1 plus 2 times the group x plus 2, which means x plus 2 over 1 plus 2x plus 4, so 2x plus 5. So the domain for this thing, f composed with f, we have two issues again. First, x must be in the domain of the final formula. Which means x can't be negative 5/2. And then, in addition to that, x must be in the domain of the inside function, which is f. And f was 1 over x plus 2. So x cannot be negative 2. So again, it's not because of the x plus 2 in the numerator, it's because the input x has to go into the function f first, and negative 2 is not a valid value for the domain of f. So we have x such that x is not negative 5/2, and x is not negative 2, but anything else is fine. So a few more examples here. It's not that the finding the formula for the composition is that complicated, but finding the domain is something new from the previous math course. So hopefully that's starting to make some sense. So here we want to find f circle G and G circle G and their domains. So f of x is x squared plus 4, g of x is square root of x minus 2. F circle G, just the formula. First we'll replace g of x with its pattern, which is square root of x minus 2. And then we want to use that square root of x minus 2 as the input for f. So we take that square root group and square it and add 4, which we can rewrite as x minus 2 plus 4, or simply x plus 2. For the domain, though, we have two issues. X must be in the domain of the final formula, which was just x plus 2, so that's no problem. But before that, x has to be in the domain of the inside function, which in this case is g. So x must be in the domain of g. And in that case, we need x minus 2 to be greater than or equal to 0. So we get anything from 2 to infinity. So even though the final formula looks pretty simple, x plus 2, the domain for f circle G would only be 2 to infinity, because before we can get to the final part, we have to first pass through the function square root of x minus 2. Then G circled G, this one's going to look a little strange. We have g of x, so we'll replace the inside g with its formula, which is just x minus 2. And then this is telling us use square root of x minus 2 as the input for g. G says take the square root of the input minus 2. And this time the input is the square root of x minus 2. So we've got these nested square roots for g composed with g, which looks strange, but that's what we have to do. And now for the domain, this one will be the trickiest of them that we've seen so far. Let's do this first. So we know that x has to be in the domain of the inside function, which is g. And we just above figured out the domain of g was 2 to infinity. And then additionally, x must be in the domain of square root of x minus 2 minus 2. And that's going to be trickier. So we need x minus 2 to be greater than or equal to 0, which we already took care of from g, and we also need square root of x minus 2 minus 2 to be greater than or equal to 0, which means square root of x minus 2 has to be greater than or equal to 2. If we think about that graphically, that's the square root graph shifted over 2. And we want to know where that graph is above 2. So it looks like once we're past 6, that would be good enough. If we square both sides of this, we'd have x minus 2 greater than or equal to 4, which is x greater than or equal to 6. So that works just fine too, just squaring both sides and continuing. Or you can think about the graph of square root of x minus 2, and where is that greater than or equal to 2. So the domain, keeping these two things in mind, if we want to make sure we satisfy both of them, it would have to be 6 to infinity. In example 6, we're going to kind of reverse what we've been doing so far, and instead of taking two functions and composing them, we're going to be looking for a way to compose two functions to create the given function. And what you want to think about is order of operations in problems like this. What you want to notice is, for example, in the 6a, we've got 2 minus x cubed, and then that whole group is raised to the 7th. So what I would think of as the inside function would be that we've got 2 minus x cubed, and then the outside, or the thing that happens second or last, is raising to the 7th. So if we're looking for f circled G, the second one is the inside, and the first one is the outside. And for the inside, we're thinking what happens first. And for the outside, we're thinking what happens last. So we could think if we take f of x to be the outside thing, raising to the 7th power, we'd have x to the 7th for the outside function. And then the inside, we could have 2 minus x cubed for g of x. That would be option 1. Option 2, sorry, my spacing is kind of strange here. Option 2, we could have maybe the first function just is x cubed. And then it'll look more complicated, but if x cubed is the thing that happens first, the outside we would take 2 minus that input and raise it to the 7th. So another option would be f of x equals 2 minus x raised to the 7th, and then the inside, the thing happening first, is let's cube that x first and then put it into the function. So those are 2 ways to write some functions that could compose to give you h. In the next one, it's not as easy to break down 2 different ways because x shows up in both terms on the inside. So in the next one, the most obvious option and the only easy option would be for the outside to be the absolute value function, and then the inside to be 2x plus 7x squared. So we would want to take f of x to be the absolute value of x, and g of x to be 2x plus 7x squared. You can double check that all of those work the way they're supposed to, but they'll work just fine. Then we've got an application here. It's saying in example 7, the spread of oil leaking from a tanker is in the shape of a circle. If the radius r in feet of the spread after t hours is radius as a function of time is 200 times the square root of t, find the area as a function of the time. This kind of composition will happen frequently when we're talking about geometry that we want related to time. So we can think, well, I know how to relate the area to the radius, and I know how to relate the radius to time. So by doing a composition, I can relate the area directly to time. So the idea is that area is pi times the radius squared for a circle, and that the radius is 200 times the square root of t. So area as a function of t directly would be pi times 200 times the square root of t squared. Better yet, I could write area as a function of r is pi r squared, and r as a function of t is 200 square root of t, so I'm focusing on what my inputs and outputs are. And then I would have a as a function of r as a function of t when I compose them would be pi times 200 square root of t squared. Right? So a as a function of t would be 200 square root of t squared times pi. So we'd have 40,000 pi pi times t for area as a function of t. So we can kind of eliminate the radius as directly. We can just go directly from t to area if we want to. Then we've got a graphical example that's a little bit different from anything we've done so far. So if I've got the graph of f and the graph of g given, and assume that each tick mark is just one unit, if I want f circled g of 1, this kind of thing really helps us understand what's going on with this composition. First, I find g of 1, and that means use x equals 1, find y on the graph of g. So when x equals 1, the y value from the graph of g appears to be negative 1. So I get negative 1 for just that g of 1 value. So then what I would do is I would replace g of 1 with negative 1. So in symbols, g of 1 is the same as negative 1. So if I wanted f of g of 1, I really want f of negative 1. And that's telling me then use x equals negative 1, find y on the graph of f. So it's two steps. First I use x equals 1 to find y on the graph of g. Then that y value becomes my new input, or my new x value. And I go to where x is negative 1. And I find the y value on the graph of f that also appears to be negative 1. So f of g of 1 is negative 1. And hopefully that process made some sense. Let's do a couple more. G of f of negative 3 says first, for the inside part, use x equals negative 3, find y on the graph of f. So when x is negative 3, find y on the graph of f. That appears to be 1. So this is asking me to find g evaluated at 1, because f of negative 3 is 1. So replace f of negative 3 with its value, that's 1, and then do the second step. Now take 1 as my input and find the y value on the graph of f, or sorry, on the graph of g, and we just did that. And that is negative 1 also. Lastly, let's find g of 2. So I'm going to use x equals 2 and first find the y value on the graph of g. That appears to be 0. Leave the outside g as it is and replace the inside g of 2 with that y value 0. That y value becomes your new x value now. It's the input, or the x value, for the graph of g. So I'm on the y-axis and I go look for the y value. Looks like negative 2. So again, this is use x equals 0, find y on the graph of g. And we saw that was negative 2. One more application here, just a purchasing application. So we have a $50 coupon from the manufacturer for the purchase of a cell phone, and the store where we are purchasing the cell phone is offering a 20% discount on all cell phones. Our X is going to represent the regular price of the phone, And what we want to do is eventually here look at applying both discounts and figuring out which order makes more sense. Applying two discounts is the same as applying two different functions. So we're looking at a composition and we want to figure out which composition is the better deal. So first, we'll suppose only the 20% discount applies. Find the function f that models the purchase price of the cell phone as a function of the regular price. So if it's only the 20% discount, then what we're doing is we're paying 80% of the price. So I'm just going to do f of x equals 0.8 times x. You could do x minus 0.2 times x. That would be the same thing. You're going to eventually get a simplified formula to 0.8 times x. And if only the $50 coupon applies, find the function g, so a different function, different name, that models the purchase price of the cell phone as a function of the regular price. A coupon would just be subtracted from the regular price. So that would be x minus 50. So then C is where we get into the composition. If you can use the coupon and the discount, then we either have f circle g or g circle f, depending on the order in which they're applied. So let's look at both compositions. F circle g would be, think about, so the inside function happens first, so that would be the coupon and then the discount. That's going to look like f of x minus 50, which would be 0.8 times the quantity x minus 50, which would be 0.8x minus 40. Or, if we go the other order, g circle f, in that case, the discount is first and then the coupon. And that would be g of 0.8 times x. And g says take the input minus 50, so we'd have 0.8x minus 50. So if we're comparing those, this is the lower price because we're subtracting more. It's the same 0.8x, but then we're taking 50 away. Instead of, after simplifying here, we'd have just 40 away from 0.8x. So this is the lower price, which we could reason out, but it's nice to see in symbols as well. It makes sense that we would want to take the discount off the greater price and then subtract 50 rather than subtracting 50 and taking the discount off the lower price. Alright, so hopefully these compositions are making sense. The next thing we're going to look at are what are called inverse functions, and then we're going to be looking at exponential and logarithmic functions.